Hi guys, so in this lecture we'll be taking on some more examples of skew conformers, Gaussian, fully eclipsed, partially eclipsed, staggered, and we'll then look into a concept called Gaussian effect. Okay, so let us start. So we have example in which we have to make the most stable conformer of this following compound 3 hydroxy propanol. Okay, so for the same we have a structure like OH, and across this carbon or across this sigma bond we have to consider the rotation. C double bond OH. Okay, so let us start from this carbon itself. We'll have C here. We have hydrogen, let us put OH here and hydrogen here. And the second carbon we have 2 hydrogen and a CO2H group. So again, hydrogen bonding can occur between this oxygen and this hydrogen, and this oxygen and this hydrogen. Hence this would be the most stable conformer. Okay, so next let us start with a question which is in which you have to calculate which of the following compound has zero dipole. So which of the following compound has zero dipole? Okay, so I hope you know what is called a dipole. So dipole is just if we have charges in a organic in a compound, then we can actually map that charge flowing from positive to negative in a certain direction, and if there is a direction in which we can actually map that considering all the atoms in that compound. So if there exists a direction in which charge flow can occur, so then the compound is said to have a is said to have a dipole moment. And in case where we can't find any direction of charge flowing from negative to from positive to negative, I actually made it wrong, from negative to positive, then actually it is said to have zero dipole moment. Okay, so let us consider this example. In this we have OH here and OH here. So this is an example in which oxygen atoms are 180 degree or oppositely attached to each other, so it will have zero dipole moment, hence this is the correct option. But one thing can be seen here is according to the O, I actually made 0, but we have to check for O between O and H as well, right? So if we see between O and H, it is surely having a dipole moment, because O is negative, more having a negative, partial negative, and H is having partial positive, same in this case. So it can have a dipole moment in this direction. Okay, let us see for this example. Here we have, in a sawhorse projection, we have Cl here and Cl and HH here. So obviously this is also having a dipole moment. Why? Because we can see, and from this carbon atom it is having more negative charge, so dipole moment will be in this direction. Similarly, dipole moment for this carbon as Cl is attached here will be in this direction, because Cl is having more partial negative charge. Let us look at third example. Here we have so in this case dipole moment would be 0. Why? Because if you see that if you make the sawhorse projection of this, you can easily see that this hydrogen, this will be partially positively charged, this will be partially positive charged, same for this. Similarly, in between these two atoms there would be no dipole moment, as both the atoms are relatively at the same electronegative level. So in all the cases, as if you draw the vectors, you can see that this dipole moment for between this carbon and this hydrogen would be in this direction, between this and carbon and hydrogen would be in this direction, between this carbon and hydrogen it would be in this direction. Similarly for all these carbons, for all these atoms. So net value for this would be 0, and for this would be 0, hence the dipole moment of the complete compound would be 0. Okay, so let's take important example. So because of this example I am going to explain the next topic to you. So if we have something like this and we have to make rotation between this carbon bond and carbon and nitrogen bond, so how do we make it? We start looking from here. So we have nitrogen here, we have a lone pair here, we have two hydrogen here, and then we have a carbon at the back of this. Let me make it more clear. We have a lone pair also here. Okay, so this is this carbon atom, this circle. So here we have, this would be the structure. And why did I place the CS3 Gaussian to this lone pair? So this concept only is called Gaussian effect, so which says that the lone pair and the most bulky group must be Gaussian to each other. Okay, so lone pair and the most bulky group must be Gaussian to each other. Okay, as lone pair is the least sterically hindered group, and lone pair is the most sterically hindered group. Is I beg your pardon, is the least sterically hindered group. Hence we place it with the most sterically hindered group, so that both the effects kind of cancel out each other. Is the least sterically hindered group. Okay, so let us see some important facts. Okay, so to see the dipole moment of this compound, to see dipole moment of Dietermach Cl here. So then if conformers are possible, then by rotating it, dipole is possible of Gaussian form. Okay, so if this is the compound I give you, so you can actually rotate it across this bond to see that if dipole is possible in any of the other forms, particularly in Gaussian form. So if it's possible, then the overall dipole moment of the compound would not be 0. Okay, so what I mean is, if you draw the staggered, this is the staggered Sawhorse projections. If you draw the staggered Newman projection, you would have something like H Cl and again Cl H and H. For this, mu is obviously 0, but if you have to see the mu, if you have to see the dipole moment of the overall compound, then you can actually rotate the bond and see. So by rotation, you can actually rotate the compound. So if I rotate this by, let's say, if I have by rotation, I can actually get this type of a ring in which I can get Cl, H and H, and Cl, H and H here. So this mu is not equal to 0, hence the overall compound dipole moment, this implies overall dipole would not be equal to 0. Okay, and this brings us to the end of this lecture. So in the next lecture we'll be seeing, before that, let me actually tell why the dipole moment of this compound is also not 0. Okay, so if we have something like O and H here, then actually mu for this compound is 0. But if we actually convert it into something like this, if we have, then the mu would not be equal to 0. Okay, so the overall mu would not be equal to 0. And I suppose I gave you an example before this in which you were asked to compare in which of the compound mu would not be equal to 0. So I took this example and explained here as to why mu would not be equal to 0 of the overall compound, because this chlorine can actually rotate itself across this carbon bond, and the overall mu for this compound would not be 0 in other conformers of this compound. Similarly, mu for this compound overall would not be 0. Okay, and mu for this overall compound would always be 0. You can try and actually rotate the bond in any direction. The reason why it's not 0, because at individual carbon level only the vector addition at that individual carbon level is 0. So howsoever you rotate the bond, it would always be 0. Okay, so this brings us to the end of the lecture. So in the next lecture we'll be taking on cyclic compounds, conformers of cyclic compounds. So till then, good luck and goodbye.